Hello again. Today our topic is insertion sort. The basic idea of insertion sort is that one element from the input elements is consumed in each iteration to find its correct position, i.e. the position to which it belongs in a sorted array. It iterates the next element in the array. If the current element is greater than the largest value in the sorted array, then it leaves the element in its position and moves on to the next element. Otherwise, it finds its correct position in the sorted array and moves it to that position. And this is done by shifting all the elements which are larger than the current element in the sorted array to one position ahead. The insertion sort steps are as follows. The first step involves the comparison of the element in question with its adjacent element. If the element in question can be inserted at a particular position, then space is created for it by shifting the other elements one position to the right and inserting the element at the suitable position. The above procedure is repeated until all the elements in the array are sorted. Suppose that we have the array A. Here we have the indices of the elements in the array. We start by 2. We copy it, for example, a location key, and we compare it with 4. Since 4 is greater than 2, then we shift 4 to the right one position, and since we haven't any more elements to the left, we insert 2 in its position. Next, we consider 6. Again, we copy it to key, and since it is greater than 4, then nothing is changed since 6 is in its correct position. Next, 8. Again, we copy it to key and compare the key value with 6. Since 8 is greater than 6, then nothing is changed. The next element under consideration is 3. Do you see the part of the array before 3 is sorted? And our task now is to insert 3 in its correct position. First, we copy the element into the key location. Next, we compare 3 with 8. Since 8 is greater than 3, then 8 is moved here. We compare 3 with 6. And again, since 6 is greater than 3, 6 is moved here. Next, we compare 3 with 4. We move 4 here. We compare 3 with 2. And since 3 is greater than 2, then we insert 3 in its position. The next element under consideration is 5. We make a copy of 5 into the key. And the purpose of this step every time is to create a free room or location for the shift operation. We compare 5 and 8. Since 8 is larger than 5, we shift 8 to the right. Next, we compare 5 with 6. 6 is shifted to the right one position. We compare 5 with 4. Since 5 is greater than 4, then place 5 in its correct position. The last element is 7. We copy it into key. We compare the key value with 8. 8 is greater than 7, so we shift right 8. We compare 7 with 6. Since 7 is greater than 6, we place it in its correct position. And here we have the sorted array. In general, if we have array A and now A sub I is under consideration, all the elements before A are sorted. And our task now is to insert AI in its correct position. We copy AI into location K to free this location for shift operations. Next, we set up a counter j initially equals I minus 1. So initially it points to the adjacent location of AI. Next, we compare k and a sub j. If k is greater than or equal to a sub j, we are done. If k is less than a sub j, then we move a sub j to a sub j plus 1, and we decrement j. We continue this procedure while the condition j greater than or equals to 0 and a sub j greater than the key. If this condition is true, we move a sub j to a sub j plus 1, and we decrement j. If this condition is false, we are done and we insert k into a sub j plus 1. Really, why j plus 1? Because in the last iteration of the loop, j was decremented by 1. After that, we move to the next element and repeat the same procedure. Here we have the pseudocode for insertion sort. First, we have the external loop for I to n, a sub I stored in temporary location, for example, key. J is initialized to I minus 1. Now these statements are performed while this condition is true. We move aj to aj plus 1 and decrement j. When the condition becomes false, we insert the contents of the key into aj plus 1. After that, we loop again with the next element. Again, the idea here is as follows. In each iteration, we consider a new element in the input array. All the elements before it are sorted. If this value is greater than the adjacent value, then we are done and we move to the next location. If the element under consideration is less than the previous one, then we have to organize the loop in order to find the correct position for this element. For this purpose, we copy the contents of this location into K, freeing a space or room for the elements to be shifted to the right. We set up a loop starting from I minus 1 and start scanning backward for the position of the element. Here we have the Python program for insertion sort. Here is the external loop for I. A sub I is moved to K. J is initialized to I minus 1. While this condition is true, j greater than or equal 0, and key value less than array sub j, we perform these two statements. We move array sub j to array sub j plus 1 and decrement the index j. When this condition becomes false, we insert the element into its correct position. And again, here we have j plus 1 because in the last iteration of the while loop, j was decremented by 1. In the insertion sort, we have two loops. So the complexity big O is n square. We have the worst case when the array is sorted in descending order, for example, 40, 30, and we need to sort it in an ascending order. And we have the best case if the array is already sorted, for example, 5, 10, 20, 30, 40. And in this case, big O is n. Insertion sort has an advantage over bubble sort if the array is almost sorted, or for example, it was sorted before, but now unsorted. Consider the sequence 2, 4, 6, 8, 10, 15, 9, etc. So in all these cases, the internal loop will not act, and we need only one comparison to switch to the next element. only here we need to insert it in its correct position. And again, for these elements, the internal loop will not act, and it's needed for inserting this element in its correct position, etc. Suppose, for example, that database X was sorted 4 months ago, and during this time, several elements were added to the database. In this case, we will have several fractions of the database that are already sorted. In this case, the performance of insertion sort may be better than the performance of other sorting algorithms. For today, that's all. Thank you.